Hello and welcome to Algebra II with Mr. Clausen. Today we are going to expand our knowledge into exponential and logarithmic equations. And specifically I want to go over examples of how to solve exponential equations, and we'll use logarithms and technology as a couple different examples of how we can do that. I also want to go over how to solve logarithmic equations, specifically using the change of base formula as well as other variations. And then I will look at a third skill where we can apply properties of logarithms to solve an equation. So with that said, I'm going to go and look at our first example here. And one of the things I want to point out, and one of the really practical uses of logarithms, is that if we see a exponential model like this one here, 12 to the y minus 2 power equals 20, one of the things that you can do in a particular situation like this is take the log of both sides. Now the base isn't necessarily important. You can go and pick the base depending on what you want to do. But in this particular situation, what I'm just going to do is say log of 12 to the y minus 2 power equals log of 20. And the reason that I bring this up and that we look at this is a lot of times when we're trying to solve an exponential equation and the variable is in a power form like this, this can be really difficult to deal with. All right, and so one of the very practical things that we can do is that if we apply a log to both sides and we just apply it in the situation, this is algebraically allowed. And then what we can do then is take the power property of logarithms and we can pull this out front. And we can say, for example, that y minus 2 times log of 12 equals log of 20 is that now if you want to solve for a specific value of y, we can just simply divide both sides by log of 12. Log of 12. These would cancel. And then we would get this new y minus 2 equals log of 20 all over log of 12. And then if we wanted to add 2 to both sides, we could just simply cancel that out. And we would get y is equal to log of 20 over log of 12 with 2 added to both sides. And so what we would get as a result is that y is equal to 1.21 plus 2. And we would see that y is approximately equal to 3.21. And so this can be a way that you can solve for more complicated variables more easily using things like the properties of logarithms and such. And the same thing could be applied to this given example. We could say log of 6x to both sides. We could say log of 4565. You know, apply the same idea, pull the x out, go and get x is equal to log of 4565 and log of 6. And then we can see that x is equal to 4.70. And what I want to do is I want to take a quick second and just show you how you can apply the same idea to solving exponential equations in Desmos. And so what I want to show you here is when we have an equation like 6 to the x power and then we say that this is equal to 4565, all right? When we look at this particular situation, it's not necessarily going to tell us what it is. I mean, we can go and we can click on the equation here and try to see where things kind of pan out on the line. And it looks like it's close to 5, but it doesn't give us an exact value. Desmos doesn't have the ability to really analyze that. But what I am going to show you here, though, is that if we go and we say something like y is equal to the 6 to the x power, And then we also say y is equal to 4565. What I want to point out is that we can do the same thing that we've done in the past in terms of using multiple equations to describe a system. And so if you ever want to find a solution to an exponential equation, you can just split both in half on each side. You can zoom out until you see 4565. And what you will notice is that the intersection of these 2 points are going to be at 4.70 for your x value, which is exactly what we did before. So just another tool to keep in your tool bag. All right, moving on to our second skill, I want to talk with you a little bit about solving logarithmic equations using the change of base formula. And one of the things that can be really practical about a situation like this is that, let's say we have to solve for log base 4 of 8, all right? And one of the really unique things that the change of base formula allowed you to do is, back in my day, most calculators didn't have the ability to pick your base. Like, you just kind of had to deal with this alternate method. So we could say that log base 4 of 8 was equal to log base 10 of 8 all over log base 10 of 4. And if you have a calculator where you can put in your own base and do that, or if you have an old-fashioned calculator like mine, or when I was in school, you could plug both of these things in and it would give you the exact same value, all right? And that's just, the nature of logarithms lends itself to this. But one of the things that you can do when we are trying to go and we're trying to solve for this particular circumstance is that we can actually solve for a given value using this. So if we say log base 10 of 8 divided by log base 10 of 4, what we find is that this is equal to 1.5. And one of the things that sometimes gets asked is, like, let's say you have a log base 4 type function, and then you're asked to change this to, let's say, base 2, right? Because we've talked about base 2 a little bit. Log base e, log base 2, and log base 10, I'd say, would be the 3 most common types of base logarithms that we deal with. So if we wanted to change this to log base 2 and have all the other values correspond to it, what we can do is that we can go and rewrite accordingly and say, for example, log base 2 of x is equal to 1.5. So if we want to still be able to go and rewrite this logarithm but still have the same output, now what we can do is that we can solve for x. And simply how I would do this is that, you know, if you use the change of base formula to find this and then you need to rewrite it, I would just take your answer that you have here, rewrite the equation, and then solve appropriately. Like with the pH example that I had in a previous video, I would take log base 2 and I would take both sides to the second power, because 2 to the power of log base 2, these are inverses to each other. If you take inverses of each other, they cancel and equal 1. And then you'll see that x is equal to 2 to the 1.5 power. And if we go to the square root of 2, or we could say 2 to the 3/2 power, this would be equal to the square root of 2 to the 3rd power, or 2 square roots of 2. And so if you wanted to rewrite this logarithm accordingly, we could say that it is equal to log base 2 of 2 square roots of 2 is the same thing, or has the same output, I should say, as log base 4 of 8, and so on and so forth, okay? And you may want to do this if you are trying to switch things to a different base. There are a few applications where you can do this, but we're just kind of breaking apart and looking at all the different applications of logarithms here and what you can do with them. So hopefully this gives you a good example of that. Now let's look at one other process here, all right? In this specific application, I want to talk about how to use properties of logarithms to solve an equation. So now, one of the things you have to be careful about here is that now we have this really big conglomerate of logarithms here. And even though it says log base 10, you can't take the whole thing to the power 10 to the power of all these logs, or you could try, but it would get really messy. And so what you want to do to start something like this is that you want to get all of your logarithmic parts on one side, and you want to get your constants on the other, or at least that would be my strategy with this particular problem. And the reason I would do this is that if you get all the logarithmic parts on one side like it is in this particular problem, then I can start looking at the properties of logarithms and see how I can simplify this, okay? Because this is very much expanded, so now I'm going to start putting things together and see if I can find some way to make this a little less messy. So the first thing I see here is I see a 3 in front of this log, so I'm going to load up the trebuchet and apply the power property here, so that I get log of x to the third power minus log of 6 plus log of 2.4. And then I think what I would do here is that I would go and I would combine these two. It doesn't really matter which one I'm doing in this case, but I would use the quotient property and combine these two guys. So then I would get log of x to the third divided by 6 plus log of 2.4. And then I would use the product property to connect these two guys together and get log of 2.4 times x cubed all over 6. And I know that this is all equal to 9. All right. And I do see that none of these logs have a base value assigned to them, so I can assume this is log base 10. And so what I'm going to do here is I'm going to give myself a little bit more space. I'm going to take everything to the inverse of log base 10, or multiply it by the power of that. So 10 to the power of log base 10, again these are inverses, and I'll get 2.4 over 6, which is the same as 2/5. Okay, so I'll just leave 2.4 here. X to the third, all divided by 6. And this is going to be equal to 10 to the 9th power. And again, these are inverses, so these cancel. And now I'm going to have 2.4 x to the third power, all divided by 6. And 10 to the 9th power. All right, and we've done all the hard work now, because what we had to do is we had to use these properties of logarithms to simplify this to one logarithm, and then we can apply these inverse relationships and get this situation. And so now I'm going to multiply both sides by 6. I'm going to divide both sides by 2.4, multiply both sides by 6, divide by 2.4. This is just the multiplication property of equality. This will cancel this, this will cancel that. And then we're going to get x cubed is equal to 6 times 10 to the 9th power all over 2.4. And if we go and we punch that into a calculator, we could get a value. But I'm going to go one step further before we do that, and I'm going to take both sides to the cube root, okay? Because what that will do is that'll get x all by itself, and I'll take the cube root of all this. And what we'll see is if we take the cube root of both sides of this, is that we'll get an x value equal to 1357. All right, and that would be your value of x given this specific circumstance. All right, and you could plug it back in and check and see if this all works out, but hopefully this gave you a little bit broader idea of how these different properties of logarithms can be applied to go and solve different exponential and logarithmic equations. And with that said, let's go do some math.